There we are. All right, lads and ladies, welcome back to College Algebra. Today is the 13th of April for you, but it's the 12th of April for me because, as I mentioned last week, I've been summoned for jury duty. So today the lecture is clearly not live. I do appreciate you coming and watching at the appropriate time. So thank you if you're doing that. Go ahead and get started. This, like we said, is MAC1105. It's section 007. It's a lecture, and it is the lecture for the day, 4/13/2021. Today we're going to learn more about logarithms. It's our last bit of new material on logarithms and exponentials, which means it's also the day that we are kind of a week out from the test. So remember, your test is next Tuesday. That will be exam, what's that for you guys? Exam 3 on next Tuesday. And then we're going to cover just a little bit more stuff before the last exam. I don't believe we scheduled the exam to be a different day. I'm going to have to double check that, but I'm pretty sure we said for next Tuesday. Anyway, today is the last bit of logarithm stuff. Last bit of logs and exponentials. Specifically, we're looking at logarithms and exponential equations. And the associated homework, there are two new things opening up today. There's a homework and a quiz. The quiz pertains to the last few sections. So here we are, homework 21, logarithm and exponential equations, and quiz 7. So homework 21 and quiz 7 are open. Homework 21 and quiz 7 are open, and they will be due next Tuesday, the date of the test. I also have a little review put together for you guys that I'll make available. Is there any other announcement-y stuff? I don't think so. I think that's the bulk of it. Remember last time we talked about logarithm properties. These are ways that you can manipulate logarithm expressions. Those are going to be important here for some of these problems. But we're going to start off with the basics. And remember the very basic here. Very basic idea is remember, like you have a to the x is equal to y means the same thing as x equals the base a logarithm of y. And the two tools, two new tools are take logs of both sides. It's like our new operation. It's our first new operation. We use it to solve exponential equations. We've seen a little bit of that, but we didn't usually use that terminology. The other thing you can do now is exponentiate on both sides. And here, exponentiate means to stick in the exponent of. And really, these are kind of how you go back and forth from this to this. You take the base a logarithm of both sides here. This object will just reduce to x, and this object will become the base a logarithm of y. We'll see lots of examples. And it's this tool we use to solve exponential equations, because exponential equations look like this, and we want to get the x down. We want to solve for x. So we go from something like this to something like this. On the other hand, if you had something like this, and you needed to solve it for y, the way you do that is to put this in the exponent of, right, a raised to the base of whatever your logarithm is. And on the right-hand side, the base a exponent and the base a log will cancel. But that's it. That's the basic idea. So examples. Sort of the simplest example we can think of is something like 2 to the x minus 5 equals 12. So I want to solve this. Our goal is to take this expression and turn it into something that looks like one of these. So then we can use one of these to solve whatever it is we're looking for. The variable that I'm trying to solve for is in the power, like here. So I'm going to want to get this piece alone, and then I can take logs to transform it into that. So my first step is to just add 5 to both sides. If I add this 5 to both sides, then the left-hand side will just become 2 to the x. And the right-hand side will become 12 plus 5 is 17. And then here's the cool step. I'm going to rewrite this like this. And we could just jump straight there. I could take the base 2 logarithm of both sides. Here's what that would look like using the take logs operation. I would have the log base 2 of 2 to the x equals log base 2 of 17. And on the left-hand side here, the base 2 logarithm of 2 to the x. Remember, the base 2 log is the inverse of the base 2 exponential. This is that whole idea. This just simplifies to x. So this is x equals, and then the right-hand side we leave alone. That's the base 2 log of 17. And then you could use your change of base formula to rewrite this as ln 17 over ln of 2. If you're working on one of the older calculators, that's what you would want to do. There's also another way to go through this process that takes you immediately to this answer, which is kind of nice, depending on what you're trying to do. So either of these would be exact answers, right? You could tell me that the solution here is the base 2 log of 17, or you could tell me that the solution is the natural log of 17 over the natural log of 2. But if I asked you to give me a decimal approximation for that, you would use your calculator. The natural log of 17, close parentheses, divided by the natural log of 2. It's about 4.087. So if I asked you to round to the nearest thousand, this is what you would give me. I'm going to show you another way to solve this equation now. I'm going to show you the way that takes you straight to this answer, and it's also going to kind of have you think about some of the other properties of logarithms, because those properties we need to become really comfortable with if we're going to solve more complicated equations. All right, turning the page in about 4 seconds. The magic of logs is that they get variables or powers down out of powers. In terms of like the algebra, the reason we like them so much is because that's really what they do. So another solution to the same problem, to 2 to the x minus 5 equals 12. We can start by adding 5 to both sides again. We always kind of need to do that. We got to isolate the exponential term first. So this 2 to the x is the exponential. That's always going to be your first step. Isolate that as best you can. Now I'm going to take an ln of both sides. And this is more along the lines of what we generally do solving. So I'm going to take again, only this time, instead of using the base 2 log, I'm going to use the natural log. I'll take the ln of both sides. That gives me the ln of 2 to the x equals the ln of 17. Again, this might feel weird, like why do this when the other way works? Because this is the more general procedure. This is what will work for more shit, more complicated stuff. So this is kind of how we need to learn to think of it. So we've taken the ln of both sides. That is allowed. It's one of those things that you can do to equations. Like you can add 5 to both sides. You can take the ln of both sides. It is a kosher operation. The ln of 2 to the x can be cleaned up using the following rule. Remember log properties? One of them was, I think we called it item 2, was that the base a log of, a power, something like x to the y, is equal to y times the base a log of x. And the way we said this is that powers inside come down and become multiples outside. We looked at a handful of log property problems like that last Thursday. So inside here, the natural log of 2 to the x, the x is a power. That power can come down as a multiple, precisely like this. This guy jumps down. You have to have something that is a pure power inside. Like if there was a +1 in here, ln of 2 to the x +1, then I couldn't bring the x down. It has to have everything inside be a single chunk raised to that power. But that works fine. And then over here, I still have the ln of 17. And then finally, just straight up algebra. Remember that ln of 2 is just a number. It's just a number. It's the exponent of e when you get 2 out. It's like 0.6, just a number. So we can divide both sides by it. You divide both sides by the natural log of 2, and you get the natural log of 17 divided by the natural log of 2, which is the answer we got the other way, remember? When we solved and then used the change of base formula. This is the better way. To solve these problems. It just is. So I'm going to show you some examples from your homework. We'll take a look at 1 or 2 exponential equations there. Some problems of this sort you may recognize or may be similar to things that we saw back in the half-life radioactive decay type problems, because now you can solve those equations that show up there exactly. You don't have to use your graph or your table. You can find the exact solutions really nicely. Let's do it. Okay. So they're starting with logarithmic equations there. I don't want to do that. So this is that sort of vibe. You could look at that or that, or any one of these. Those are getting into logarithmic equations. All right. Wow, just a very small number of forms here. All right. So you can solve this equation graphically, and they ask you to do that, but then they also ask for an exact solution given symbolically. So we're going to solve the equation f of x equals g of x here symbolically. And say let f of x be, and I'll probably change this just a tiddlywink. How about 10 to the 1.3x equals, what kind of number over here? Oh no, sorry. All right. F of x equals that. And g of x equals about 37.5. And I want to solve the equation f of x equals g of x. Classic problem, we see this shit all the time, right? They say to solve it graphically and then to solve it symbolically. I'll show you very briefly how to solve it graphically since we've done this before. You turn on your calculator. You hit y equals. We're trying to find where this function is equal to this function, which means we need to graph both of these and see where the graphs hit. The x value where they intersect would be the solution to this equation. So I've got 10 raised to the power of, and you should put this in parentheses, especially on a TI-83, 1.3x. So 10 raised to the 1.3x, that's my first function. My second function, y2, is 37.5. I can graph them. My scales might not be such that I can really see what's going on. Yeah, I can't see jack shit, right? Well, why? Because this is 10 to the 1.3x. 10 to the x, that's going to grow pretty quick, like on its own, right? You feed in x equals 1. This is 10 to the 1.3. So this function is growing way too fast for this viewing window. We need, this thing puts out bigger y values. In fact, the y value that we're trying to find this thing equal to is 37.5. That's not even visible here. So I think a better picture would be like from -10, say, to, I don't know, 80. Certainly something bigger than 37.5. I'm going for something about twice as big. We can keep the scale at 1. We can keep from -10 to 10 on the, oh no, those are x's. Okay, sorry, x's will go -10 to 10. We'll keep those. But the y value needs to go up to like 80 at least. Right? So the smallest y value on my graph is -10, largest is 80. My x's run from -10 to 10. We can take a look at this graph now. And it should be a little bit more intelligible. Particularly, we should see that second function. There's more we can do, right? You notice it's still growing way too fast. So I can change my x max to like 4 and probably still catch everything I need. Yeah. And there's really no benefit from having it, you know, -10. So if you really want to zoom in on the fun spot, that's not bad, right? Now we can see. So learning how to play with the window settings is important. You can try messing with the zoom function. I don't like it as much, but there are guides all over YouTube. Here is our trace function. It looks like 1.18. This x value is too small. 1.23. This x value is too large. So I'll come back here to 1.18. We'll just say second window to go to table settings. I'll start the table at 1.18, and I'll tell it to take steps of 0.01, and then I'll go to my table, and we can play around until we're happy. I'm seeing right here about 1.19. Right. So graphically, from the TI-84, when we draw the picture, I look for where the two things hit. This appears to be x equals 1.19. So x, approximately equal to 1.19. That's our solution. And graphically, it's a good estimate. It's not perfect though. And if I want to solve it symbolically, that's kind of the big point of this week. I probably misspelled symbolically. Symbolically, one L there. I'm not sure. Symbolically, f of x is equal to g of x. In algebra terms, this is just 10 to the 1.3x equals 37.5. And here is where our new technique is going to become really useful. We take the ln of both sides again. Take logs. Truth is, you could use any log here. That's why you see me saying take logs, not take ln necessarily. You could take other base logs, and they work the same way. You just have to be mindful. But everybody's calculator has an ln button. The ln is the natural log, so it's the natural choice to use. This is the ln of 10 to the 1.3x equals the ln of 37.5. Take logs, put both sides inside the logarithm. Take the logarithm of both sides, just like you take square roots of both sides. And again, here, this log property is going to be useful. If you have a log of some shit to a power, as long as all the shit is being raised to that power and there's nothing else inside the log, the whole power, whatever it is, can get its happy ass down in front. So this is 1.3x times the natural log of 10 equals the natural log of 37.5. That's it. So now you can solve for x. Done the hard part. You got the x down out of the power. That's what makes these problems hard. And until we had logarithms, we didn't have a tool for doing that. All right. I want to solve for x. So I can divide both sides by the natural log of 10. I can divide both sides by the 1.3. You can divide by both of them at the same time. And on the paper, it's easier than it is on the calculator. So symbolically, it's nice. Dividing by 1.3 times the natural log of 10. I have here 1.3 times the natural log of 10. That's it. That's my answer. And if you want to see how good a job we did with the graph, let's forget what the quiz is. Just turn it off. I want to see how good a job we did with the graph. We can. Here's the natural log of 37.5, close parentheses, divided by open parentheses, because I've got two terms down here. So whole bottom goes in parentheses. 1.3 times the natural log of 10. Now I have two parentheses to close. 1.21. So we're not off by too much. 1.37.5, 1.3. I'm saying here, yeah, 1.21. So our table guess is off by more than I would have thought. 1.211 if you want. We can go back and look at our table again. What was I saying here? Yeah, this looked like it was too big. Oh no, I was misreading. Here, 35. Yeah, no. This is supposed to be 37.5, right? So here's 37.4. Yeah, no, I'm sorry. I just wrote our guess down wrong from earlier because I was looking at 35. 37.5 is what we wanted. So 1.21 is actually spot friggin' on. We did really good. I just wrote down the wrong thing. You guys see over here in this column, 37.411. That's the y value here that's closest to 37.5. My brain just saw 35 and forgot about the 7. 37.411 is definitely the closest of all these to 37.5. So that x value, 1.21, that's our guy. Yeah, so in fact, it's a really, really good approximation. It's very good. Okay, this is how we solve these equations if the variable is trapped in an exponent. There are other examples for you to play with in your homework. You will want to remember some basic facts about how to evaluate logarithms. For example, in this one, you will at some point want to know what the natural log of e is. And I invite you to try and remember that. We talked about it last Thursday. But I think the rest of these you'll be able to handle quite well. just based on what we've done so far, until you get down to number 7 here, where you see logarithmic equation, logarithmic equation, logarithmic equation. So we need to come back and talk about the other family of equations here and the other technique, rather than the take log thing, the exponentiate thing. Okay. If it doesn't bother you, I'll just continue on this sheet here. Line break. Logarithm or logarithmic equations. Let's say it either way. People know what you're talking about. I think logarithmic might be more jargon. Again, here we're using this fact that if you have the base a log of something, here I'll write it as x this time, is equal to something else. Call it I shouldn't call it a, and we're using a. So let me call it y. Then that means the same thing as x equals a to the y. And the way you go back and forth from this is sort of thought of happening as via the exponentiate operation. When I want to go in this direction, right? When I want to go from this thing into this thing, do it by the exponentiate operation, which means to put both sides in the exponent, and then you get to choose of, blank. In this case, it would be a, but you get to choose. So let me show you an example. If I have an expression like the base 2 log of x is equal to 4 or 3, then I can solve this for x by using this fact. And the way we use it is by exponentiating. So here the step is exponentiate base 2. I choose the same base as the logarithm. That makes life easier. What does it mean to exponentiate base 2? It means I put both sides on their own into the power, into the power of 2. I take this thing and I replace it by 2 to that thing. I take this thing and I replace it by 2 to that thing. So this power here is a 3. That is not clear. I'm sorry for my typo. And then by our properties for logarithms, this one not so obvious. This was from the second definition I gave you guys. 2 raised to the base 2 log of x, just like the base 2 log of 2 to the x, that simplifies to x. So this is just x equals 2 to the 3. And 2 to the 3 is 8. That's our solution. And you don't need any fancy ways to write it. They won't always be this nice. And again, sometimes you want decimal approximations. But the big thing is that you learn that to solve logarithm equations, you need to get the log alone, right? So a logarithm equation is an equation where your variable is inside the logarithm that you're trying to solve for. You need to get that whole piece alone, and then you need to undo the logarithm. The way you undo the logarithm is by exponentiating. You put that thing in the exponent of whatever the base was for the logarithm. If you're going to do that on the left, you got to do it on the right. You're allowed to do these operations. They're one-to-one operations. So you're allowed to do these operations on both sides of an equation. It won't change the solution. Let's try some more examples. I'll take one or two from your homework. Sure, why not? Well, okay, no, I can't. What we're going to do, we're going to say solve 2 ln of x minus 1 equals 13 for x. All right. I apologize for going back and forth between the blocky ln and the script ln. It's a habit. Yeah, ln, same ln as before, just cursive L. We need to isolate the logarithm term, which is this. So the 2 and the minus 1, they got to go. And then we're going to undo the logarithm by exponentiating. That's the but. So 2 ln of x minus 1 equals 13 is equivalent to, that's what this notation means. It's a nice notation for putting between your rows of equations. This original equation is logically equivalent to what I get if I add 1 to both sides. The order of operations, we got to undo the 1 first. So we get 2 ln of x equals 14. 13 plus 1. Then we undo the 2. So we divide both sides by 2. 14 divided by 2 is 7. And then to undo the ln, this is the magic step. We exponentiate. In this case, remember, we use the base of whatever logarithm is in play. The ln is the base e logarithm. So we exponentiate base e. And that's the magic step. So what does that look like? That looks like e raised to the ln of x equals e raised to the 7. Please don't write e to the ln x equals 7. That's not the same thing. Doesn't make sense. So each side gets their own base. Please, please. Again, by the property of logarithms, e raised to the natural log of x is just x. So those go away. You just get e to the 7. That's your answer. Now, how big is e to the 7? What is it? E is a little smaller than 3. So e to the 7 is a little smaller than 3 to the 7. 3 to the 7 is pretty big. 3 to the 4 is 81. I'm not sure what 3 to the 7 is off the top of my head, but it's, oh, here's quick. So if I want to know, I just come in here to my calculator, I hit second, and this ln button you see in blue there, it's got the e to the x thing. So if you want to type in a power of e, you hit second and then that ln button, because that's how you select the blue thing. The second is the blue, whatever color your second button is. And then we type the 7. If you're working on an 83 or earlier calculator, again, parentheses. Power is in parentheses. But here, I get 1096. 0.63. That's it. That's your answer. Again, rounding up depending on where they tell you. We're doing for time. We still have a fair amount of time left, so I can do a handful more examples. I think it would be good to look at something more complicated. I don't know if we get all that complicated. We really don't. So I'll tell you what, I'll look at one more of these kind of basic logarithm equations, and then we can do a word problem or two. Okay. Again, we're going to solve this for x. This time I'll ask you to work with 15 plus 3 times the base 6 log of x minus 1 equals how about 35? So kind of mimicking some of the later problems, putting a few of those together. Same premise as the last couple. Isolate the logarithm term, then undo the logarithm by exponentiating using the appropriate base. So if I want to isolate this term, the 15 and 3 got to go. So I subtract the 15 here. When I subtract 15 from both sides, I get 3 times the base 6 log of x minus 1 equals 35 minus 15, which should be 20. Now, if I divide both sides by 3, I get that the base 6 log of x minus 1 is equal to 20 thirds. And you should leave it like that. Please don't write this as a decimal. Just leave it like this. Otherwise, we get rounding errors, run out of trouble. From here, I now have my log term isolated. We can't divide over the log. It's not multiplication. This is the base 6 log of x minus 1. So base 6 log is a function. If you want to undo that function, you need to exponentiate. In this case, because the logarithm we're using is a base 6 logarithm, we're going to exponentiate base 6. So I get 6 raised to the power of log base 6, x minus 1, equals 6 raised to the power of 20 over 3. You can see these can get pretty gnarly in their solutions. On the left-hand side, by properties of logarithms, right, the definition really, 6 raised to the base 6 log of x minus 1 is just x minus 1. So whatever shit is inside the log, a raised to the base a log of shit is just shit. And over here, this is 6 to the 20th, 6 to the 20 over 3. And then lastly, kind of sillily, we're going to add 1. So this is 6 to the 20 over 3 plus 1. And again, you could look at a calculator representation of this. How would we type it? 6 raised to the power of, open parentheses, 20 divided by 3, close parentheses. And then you can hit enter. That's just this part. So if you want the whole thing, you type plus 1, and you see it'll take your previous answer and add 1. So it's about, it's big. 20 over 3 is quite large, right? That's like 7. So 6 to the 7 is going to be quite big. 155.717. Probably an irrational number, probably keeps going. We're just out of bits. But yeah, that's how you solve exponential and logarithm equations. There are more complicated ones of these where you have to like factor some expression, and then each of the little factors gives you an equation like this. There's all sorts of good shit that I would love to show you that requires careful use of like factoring polynomials inside of logs, that sort of thing. But the course has been softened over the years, so we don't do that at the moment. Just be aware that it will be there if you're going to take pre-calculus. These sort of things can get much headier. So this is a foundational thing. You need to get good at this. A fun fact, before I talk about number problems, word problems. The area of math that I work in, one of the coolest results, now that we've learned something about logarithms, one of the coolest things, one of the coolest, we call them theorems, all right, in mathematics, all of math. There's like 5 things I could put here that have to do with logarithms. But one of the best ones is that if you define the function pi of x, you define that function by the rule, this is equal to the number of primes which are less than or equal to x. So it's the prime counting function. We're talking about prime integers here. Then the prime number theorem says that pi of x is pretty much equal to x over the natural log of x. Specifically, as x gets bigger and bigger and bigger, this gets closer and closer and closer to this. So this is a really good way to count the number of primes there are less than a given number. Huge deal. Can't even begin to tell you what a big deal that is. Huge deal. Other cool thing that we can now discuss. Euler's, I don't know what to call this. Call it an identity if you want. It's a very cool thing. It just has so many names. You take the number e and you raise it to the power of I times pi, where I is the thing you think it is and pi is the thing you think it is. You get -1 out, which can be rewritten as e to the I pi plus 1 equals 0. And a lot of people are way into this. Just because it's pretty, because it's got all the important constants and all the important operations. And again, it's built out of a natural exponential. It's something strange here. You're doing like complex numbers, right? Imaginary numbers. You're multiplying them by like pi, which is a weird constant from geometry. Shoving all that in the power of e, whatever the fuck that means. And then you add 1 and that gives you 0. This is one of those things that is thought of as cool because it's like, no way. You first see this and your thoughts should be utter disbelief. And similarly, this is shocking, but for different reasons. But just because counting prime numbers is so hard. It turns out figuring this out requires thinking about this. You need to think about complex valued functions, complex variable functions in order to recover this result without a lot of work. Much easier if you use complex variables. All right, story time over. A little word problem. And then I will let you guys go. We'll take it from here. They say that the concentration of bacteria in a sample can be modeled by, so, concentration of bacteria follows B of t. So it's a function of t, which stands for time, equals B0 times e to the, we call it R, kt, where t is time and hours. And B is concentration in billions per liter, whatever, okay. If the concentration increases by 19% in 6 hours, find K. by 19% and 6. Now let me change this a little bit. Let's say 12% in 8 hours, just because. Find K. Okay. What does it mean to say the concentration has increased by 12%? Well, if the initial concentration that's this initial value, that's the constant out front, that's B naught. Then increasing by 12%, we did this sort of thing. This is B naught plus 0.12 times B naught. Right, this is 12% of B naught. So if you increase by 12%, add that back to the original, you get 1.12 times B naught. That's what it means to have increased by 12%. We talked all about this when we talked about rates. It's just a simple thing. So they're telling me that after 6 hours, I have this much shit. Because after 6, what did I say, 8%, just 8 hours. If it increased by 12% in 8 hours, that means B of 8 is equal to this. Equal to 1.12 times B naught. Right, that is what this statement says. Increased by 12% in 8 hours means, well, here's what you get if you increase by 12%. And B of t measures the amount of like the concentration at t hours. So after 8 hours, that's B of 8. B of 8 is also what you get when you plug 8 into this expression. So it's B naught times E to the K times 8. And that's what's equal to 1.12 times B naught. And now you can see where this might be going. I have here an equation that I can solve. It looks like it's got too many variables, but when you divide both sides by B naught, they will cancel. We're trying to find K, remember. So here I have an equation that I can solve for K. First, we divide both sides by B naught. 8 times K, K times 8. It's e to the 8K. That's the nice way to write that. The B naughts cancel. So you get e to the 8K equals 1.12. Now you take the natural log of both sides. Again, you could choose whatever log you wanted, but the ln is the nice one, especially since the base here is e. You get ln of e to the 8K equals the ln of 1.12. As before, the 8K comes down, the power, but the logarithm of some shit raised to some other shit. That power, that other shit, can come down front. So as a multiple, 8K times the natural log of e equals the natural log of 1.12. And you could carry this term around. You could divide over by it and divide over by the 8, but you'd be foolish to not recall that the natural log of e is an easy number to find. This is 1. You're asking, to what power must you raise e in order to get e? You must raise e to the first power in order to get e. So this just says 8K times 1, or just 8K is equal to the natural log of 1.12. And now we divide both sides by 8. And you could be dividing by 8 times the ln of e here. It would be fine. It would just be extra junk to write. if the base wasn't e, if these didn't have the same base, then you would have to carry that term over. So it's not bad if you do it. Just a little redundant. And that's it. So we can here give a decimal approximation if we want. Careful with parentheses. So it'd be the natural log of 1.12 close it a paren divided by 8. About 0.4166. Yeah, thereabouts. So that is K. That's part A done. Again, the trick was if your function over 8 hours has increased by 12%, that means after 8 hours, the concentration is 1.12 times the initial concentration. Because the initial concentration is B0, and when you increase that by 12%, you're taking the original amount and adding 12% of that back. You add those together, you get 1.12 times B0. You set your function equal to 1.12 times B0. At this step, you recognize your goal is to solve for K, because you've got this K and it's up here in the exponent. So you need to isolate the exponential, divide both sides by B0. Miracle, it cancels, goes away. Good shit. And from there, it's just like the previous problems. We're not done yet. That was just part A. In part B, they want to know how much is left after 8.4 hours. And they want to know how much does the concentration increase by each hour? Like what is the growth rate? All right. So our function here, just for fun, after part A, we know everything about B of t. Well, almost everything. We know that B of t is equal to B0 times e raised to the power of the natural log of 1.12 over 8 times t. That's really my function. You could shove the decimal in there if you're okay with having rounding errors. But if you want it to be exact, that's your function. All right, part B says, after 8.4 hours, how many bacteria are there? Oh, if B0 equals 1.4, find B after 8.4 hours. Part B, if B0 equals 1.4, and I'll change the time a little bit. Find the concentration after 9.7 hours. So if B0 is 1.4, then we can update our model again. Now we really do know everything. This is 1.4 times e raised to the natural log of 1.12 all over 8 times t. That's the whole thing. And now I can answer you whatever you want. So you want the concentration after 9.7 hours? I got you. After 9.7 hours, the concentration is, well, B of 9.7, which is 1.4 times e raised to the natural log of 1.12 all over 8 times that time, which was 9.7. And certainly from here, it's calculator time. This is not the sort of number you can hope to crunch out by hand. I would do it like this. I would type first the e. Oh, no. So I'll multiply by 1.4 at the end. I'm worrying about the exponential part first. E raised to the power of. And then in here, you must be extremely careful. parentheses around the whole exponent. Your fraction is the natural log of 1.12. Close the parentheses for the log. You want to divide that apparatus by 8. And then you can multiply by the 9.7. This 9.7 is upstairs in this fraction, but the calculator will interpret this following the order of operations. It will do the multiplication and division left to right. So it'll do this divided by this, but then separately it will multiply by this. If you wanted to be very, very careful, you would type this as e raised to the paren, natural log of 1.12. Close the paren for the log, divide by 8, close that paren, and then multiply by 9.7, and then close the paren for the whole exponent. This is really the careful way to type this. And you get this. This is 1.4729. 472996 billion bacteria per whatever it was, per milliliter or something. That's it. There was a part C here, right? The concentration increases by how much each hour? So the concentration increases by what percent each hour? And if you were here right now, I would ask you guys, what is this asking for? After a reasonable stretch of quiet, someone would say the growth rate. The growth rate, that's what it's asking me for. Which is also like the effective interest rate, if you want to think of it like that, the growth rate. So to sort out the growth rate, remember you need to write the function in standard form. This sure as shit ain't that. This is 1.4 times e raised to the natural log of 1.12 over 8 all times t. So we need it in one constant times another constant to the t, or x, whatever your variable is here, it's t. Which means I need to handle that part. So the c is 1.4, right? That's your initial value, or b naught. This piece is where we need to work. We write this as e raised to the ln of 1.12 all over 8, all to the t. And this is using that same trick. We've used it a bunch now, the rule that a to the b times c is the same as a to the b all to the c. So I want to write this in standard form as one constant times another constant to the t. That first constant is 1.4. That second constant is e raised to the power of, open parentheses, natural log of 1.12 divided by 8. So 1.0142669. Is all that raised to the power of t. And what's the growth rate for this? It's the distance from this thing to 1. It's this thing minus 1, or the absolute value of 1 minus this thing. It's the stuff after the decimal. It's the 0.0. Yeah, so 0.0124. 669. If you don't remember what the growth rates are, growth rate, if you have c times 1 plus r to the x, then r is the growth rate. That's the idea. So here the growth rate is this, or about 1.24669%. Get the decimal place over and you get the percentages. All right. That's what I have for you guys. This is, again, the last bit of new material for exam 3. I know exam 4 is going to be very time crunched. It's going to be quite simple, and obviously we can't have it in class, but there is just a concept here that we more need to remind you of from your past classes and show you a little bit of something new. Systems of equations, systems of inequalities. So that's going to be the last bit of material that we'll talk about before the end of the semester. We're almost there. So that's it from me for you guys today. I hope you have a lovely rest of your day, and I will see you guys on Thursday.